uh, will and he'll continue on. Then I'll take over if you see there's a bullet on reliable communications, and then finally Matheus will do so the last part of the course. Okay, so let's start with the introduction. So first of all, what is it that this network is trying to accomplish? Well, we have two parties, Alice and Bob, and Alice has some quantum state that she would like to transfer to Bob. And the idea is, how can we make this happen in, let's say, a global setting or metropolitan setting or whatnot? And so the vision is that eventually we're going to have a quantum internet, which is really going to be a global network that's going to be capable of high rate, high quality quantum communications over long distances, serving just a huge variety of applications. Might have to do with security, with distributed quantum computing, sensing. What I imagine, just as happened with the classical internet, there'll be applications that some of you in your dorm rooms will come up with that we sort of researchers would never have thought of. The key ingredient to all of this is what's referred to as quantum entanglement, which you have undoubtedly been exposed to, also known as a Bell state between a pair of remote processors, Alice and Bob. Okay, and I've sort of shown the Bell state here, and what is done is the Bell state includes two qubits, and one qubit is given to Alice and one qubit is given to Bob. We can think of it that uh, it would be as if each qubit is sort of equally likely to be thumbs up or thumbs down, as I'm sort of showing here, um, in superposition. And then what we know from having studied quantum information systems is if Alice decides to measure her qubit, she's going to get either thumbs up or thumbs down. And what's really remarkable about entanglement is that ensures that when Bob goes to do his measurement, he's going to get exactly the same result. And this is what Einstein referred to the spooky action at a distance. And this was the subject of the Nobel Prize in Physics in 2022, given to these three scientists who spent much of their lifetime sort of studying and trying to understand entanglement. What I find interesting about them is that in the case of at least two of them, they were skeptical that there was anything special, but the experiments that they conducted showed that indeed quantum entanglement is very different from, let's say, what you might find in the classical world. Okay, so why the quantum internet? Um, well, there are just a variety of applications that it would enable, cryptography and security being probably the most developed in terms of quantum key distribution. We all know that there is an algorithm by Peter Shor that if a quantum algorithm that if and when it's actually sort of deployed, it will break the security of the current web. And so the idea is that although there may not be any one computer that could run Shor's algorithm, if we could distribute it among a bunch of quantum computers connected with a network, then it might be possible. Another application is high resolution sensing. It turns out to be crucial for doing sort of deep space telescopy. And in the context of communications, there's this operation quantum teleportation, which relies on entanglement for the transmission of quantum information. Okay, so that's sort of the context. And now what I'd like to do is to talk about some of the fundamentals of quantum communications that are important for quantum networking. Okay, so as I mentioned before, we have this Bell state, which is a superposition of two qubits in the 0 and the 1 state. And as I mentioned in a couple of slides ago, we know that when we go to measure one of the qubits, let's say the first one, Alice's qubit, it's going to yield either a 0 or a 1. And we're guaranteed that if it's a 0, then when we measure Bob's qubit, we're going to yield a 0 as well. And likewise, if it's 1, we would yield a 1. And this happens with equal probability, completely random. And so it can be used then to generate shared randomness across distances, which is really the fundamental idea behind quantum key distribution. But it's the key ingredient for lots and lots of other applications. Okay. But for it to be useful, we need to be able to distribute these two qubits to, let's say, parties Alice and Bob that might be hundreds or thousands of kilometers apart. I should mention there's a multipartite extension of the Bell state called the Greenberger-Horn-Zellinger or GHZ state. It consists of n qubits, and what I've written here is essentially just the natural extension from the Bell pair. It's the superposition of all zeros and all ones with the same amplitude. And this is used in multi-party QKD and again for lots of other applications. And if we think of it in terms of the thumbs up or thumbs down, here's what we would have if it were distributed between 3 parties. Okay, I mentioned that quantum teleportation is an important consumer of entanglement, and it's important for lots and lots of services. And the idea, I just want to go through to make sure you recall what it is we have Alice and Bob. They are sharing an end-to-end entangled Bell pair. And Alice, let's say she has developed this qubit that she thinks is really pretty cool. Okay. And what she would like is to essentially pass it on to Bob. Perhaps Bob has better equipment in his lab for which to study it. And so quantum teleportation is all about that. And the way it works then is that Alice entangles this star qubit with her Bell pair qubit, measures the two off, and that's going to generate 2 classical bits, let's say 1 and 0. Bob may not know anything of what's happening, may be wondering what's going on. And all Alice needs to do is to send the classical information to Bob, and then Bob can use that to decide what operation to apply to his qubit. And the result is that he will have that star qubit that Alice first started off with. Okay. What I'd like to do now is to talk about, how we're going to sort of, let's say, distribute this entanglement, or how we might be able to, let's say, transfer a qubit of information from Alice to Bob. So I want to talk about quantum communications over a single link. So we have Alice and Bob. Alice and Bob have memories. They can store qubits. There is a channel between them. It could be an optical fiber that connects Alice and Bob, or it could be just a free space link, let's say a distance of L apart. And the way that Alice and Bob will communicate is they will use photons to carry, let's say, quantum information. And there are two different approaches that have been developed for actually making this happen. They're referred to as the one and two-way quantum communication architectures. And I'm just going to sort of briefly go through each of them. And I should just mention that the this mini course is really going to focus on two-way quantum communications, and we'll talk a little bit about why. Okay, so let's look at what I'm referring to as one-way quantum communications over the link. Okay, so what Alice would do is to prepare a qubit in some state, let's say, that she wants to transfer to Bob. And then the state would be transduced from, let's say, memory to a photon. And the photon would just be passed on to Bob through the channel. And then Bob would take that photon and then essentially load the state psi into one of his memories, his memory qubits. Okay, the two-way quantum communications behaves a little bit differently, and there are a number of ways that it can be sort of uh, sort of deployed. I'm going to talk about one particular way. What happens in this case is that Alice and Bob generate a photon memory bell pair. And what I'm doing is I'm showing you the memory part, and think of it that each of those is entangled with a photon. And then what Alice and Bob do is transmit those photons uh, towards each other. And what they do is they meet at what's referred to as a Bell state analyzer. And what the Bell state analyzer will do is what's called a Bell state measurement. Then, and the result of the Bell state measurement is going to be a couple of classical bits that will each be sent back to Alice and Bob. And once Alice and Bob take those measurement results and perform operations based on them, they will share a bell pair. Okay. The reason that it's referred to as two-way quantum communications is that you have this, let's say, transfer of quantum information in one direction, but then you have to transfer classical information, namely the result of these measurements, in the opposite direction. And so, in any way, the results will be that Alice and Bob will share this Bell state. Okay, so that brings up the question. I've sort of told you how to do things, and so the question is, why aren't we doing it yet? And why is it that quantum communications is so hard? And it's because photons can suffer loss, and there is noise in the environment that can essentially sort of corrupt the quantum information, whether it's a Bell state or some qubit. And so let's start off with worrying about loss. We have Alice and Bob. They're a distance L, let's say kilometers apart. It turns out that the rate at which photons make it from Alice to Bob decays exponentially with distance. Okay, so it decays extremely fast. This is over a fiber optic channel. And I should mention that in the classical world, the decay is much slower. It's actually polynomial and not exponential. And this exponent alpha is sort of depends on the fiber technology. A really good quality fiber technology would have a smaller value for alpha than a poor technology. Okay. Now, also in the classical world, what we would do is we would send, let's say, the information some distance, and let's say when it started to become faint, we would amplify the signal. And so it brings up the question, well, why don't we do that here with quantum? And the answer is that there is this no cloning theorem that says that we cannot copy quantum signals, and therefore there is no way that we can take, let's say, quantum information and sort of uh, copy it and then sort of send it out again at let's say, high power. So that brings us to our first poll question, okay? And it's, how does the generation rate of EPR pairs decay with distance uh, when we're doing direct transmission through fiber? Okay, and question, the possibilities are, well, yeah, polynomial decrease, exponential increase, or exponential decrease, or it really just depends on the fiber technology used. Um, or, if you're not sure, you can pick E. And so we'll just wait a little bit to collect answers. Okay, so most responses were that you have an exponential decrease, and that is in fact indeed the case. Uh, Depends on fiber technology used. I can see why there might have been some responses. Uh, the exponential decay is true no matter what the fiber technology is, but of course the decay rate does depend on the fiber technology. So in a sense, there's some truth to that. Okay. Oops. So going back to, why quantum comms are so hard, let's talk about noise. Okay. And it's important to understand that qubits are very different from classical bits in that, as I'm going to show you, they're not self-protected against small perturbations. Okay, here I have a sort of a picture for a bit. Uh, let's say the encoding for the bits 0 and 1 are these red points right here. A noise might affect the encodings, and maybe the encodings might move to this right here. But it's very easy to tell what the bit is, because what we would do is we would just pick the closest red dot, and we would say, okay, well, that's what this must be. So this must be a 0, this must be a 1. Unfortunately, that's not true with the qubit because qubits can take, sort of, uncountable number of values and sort of like all over the place. And so you might have a situation where, okay, we're looking. We have 0 and we have 1, and the noise might take it a little bit uh, of the sphere, but that corresponds to a valid qubit. And so we wouldn't know whether that was what the value of the qubit was or whether it had been pushed there because of noise. The other thing is that qubits have limited coherence times. If you take any qubit memory, what you'll find is there's sort of a natural state that the memory would like to be in, and that might be what we would call as 0. And when we want it to be in the state 1, we put it into sort of a higher, let's say, energy state. And what will happen over time is that system will want to try to go back to whatever the ground state was that zero belonged to, as we see in this curve right here. And so if we look at Alice and Bob, they're, let's say, L kilometers apart. We have noise then that's introduced through the communications. The state can decohere. And what's awful with Bell states is Bell states include 2 qubits, so they decohere twice as fast. When we do these measurements and these operations that I've alluded to, they're noisy, and so it's noise just creeps in very, very quickly. So just a little table, we would have, let's say, in the case of one-way communications, the expected state is psi. In two-way, it would be this Bell pair right here. But what's going to happen because of noise is that we're going to get some kind of a 1-qubit mixed state, not psi, and a 2-qubit mixed state, and not the Bell pair. Now, the way that we sort of assess the effect of the noise is there's a fidelity measure. It's a measure of closeness between 2 quantum states. Think of it ranges between 0 and 1. 1 corresponds to complete fidelity, and as the closeness gets, as the states get farther and farther apart, we have decreasing fidelity. And so the fidelity of a direct transmission then is going to be the closeness of the receive state rho and the state psi that was transmitted. In the case of entanglement fidelity, it's between the 2-qubit state rho and the perfect Bell pair. So how do we deal with this? Well, in the case of one-way quantum repeaters, or one-way quantum systems, so here we have Alice and Bob, and let's say we have a node in the middle, and what we use is quantum error correction, and we protect the information with quantum error correction. So we might take 1 qubit and encode it in lots and lots of physical qubits for the purpose of error correction. When it comes to, let's say, this intermediate node, it's decoded. If need be, it's corrected, and then it's re-encoded and transmitted across, let's say, to Bob. Bob will decode and then put it in memory. And so you start off with the single qubit. It gets essentially encoded into lots of photon qubits, and the state is recovered if a sufficient number of the photons survive. And the probability that we're able to deliver, let's say, this logical state, the probability P will depend on the kind of code that we use. And here, one thing we'll sort of talk to this is you can sort of do this error correction without requiring any quantum memories, let's say at this intermediate node. Now, two-way quantum, what we do to deal with loss is we again introduce a quantum repeater, but we also introduce memories into this repeater. Okay, so we have Alice and Bob. This is the repeater right here, and with a bunch of memories. And then the system works as follows. There are 2 phases. In the first phase, the links between Alice and the repeater and Bob and the repeater generate link level entanglement. They generate Bell states. And so they just attempt, And if it fails, they attempt again. If it succeeds, let's say between Bob and the repeater, then the repeater and Bob have to notify each other that it worked. That's called heralding. Alice has to continue and try again, and maybe she succeeds the next time, and she and the repeater have to herald. We've stored qubits in the memory, and now we go into a second phase where what we do is perform a Bell state measurement on the two stored qubits. And that essentially destroys the qubits, produces 2 bits of classical information, and that classical information then is passed to, let's say, one of the n nodes, let's say Bob, and Bob can use those 2 bits to decide what operation to perform on his qubit, and the result will be that Alice and Bob will share a Bell pair. And now what happens is each of these links is only half the length of the distance between Alice and Bob. And so we essentially get a decrease in the decay rate. Instead of e to the minus alpha L, it's e to the minus alpha L over 2. And what this suggests is, well, we should put lots and lots of repeaters in between. And in principle, then, we could really reduce the decay rate and make it as small as we wanted. Now, the problem is that each of these nodes has to perform these Bell state measurements, and those measurements introduce noise. Okay, but in principle, if you have lots of memory, you can get essentially distance-independent entanglement rates by just adding more and more repeaters. If you only have one memory per repeater, turns out in that case, you still get the exponential decay. Okay, I'd like to say something about multiplexing before we get back to how to deal with noise. Okay. Multiplexing refers to that we can essentially sort of do things in parallel. And so in the case of, let's say, a one-way, what we can do is we take this logical qubit, we encode it into lots of physical qubits, and then we just transmit all of those qubits in parallel. Okay. And so you can think of it as sort of a form of multiplexing. In two-way repeaters, what we would do is we would essentially have, we can think of it, we would have, let's say, M sort of parallel channels between the two nodes. And at each time step, we would attempt to generate Bell pairs across all of those channels. And some of them would succeed and some would fail. And so, it brings up the question, so what is the probability that we at least get one to survive? And the answer is it's given by the following expressions, very easy to derive. If P is the probability of a loss, then 1 minus P, if P is the probability of a success, then 1 minus P is the probability of a loss. And for all of them to be lost, it's going to be 1 minus P to the power M. Okay. And so if we subtract that from 1, that's going to be the probability that at least one made it across, in which case we can use that for the next phase. The probability that K survive, well, it's just given by the binomial distribution that I've written right here. Okay, this brings us to the third poll question, which is, how many pairs can we generate in a multiplexed attempt? Where M is, let's say, the maximum number and P is the probability of successfully generating a pair. Is it M over 2? Is it the product of M and P? Do we always generate one? Or is it a random variable with, let's say, a binomial distribution? Or is it not at all clear what it might be? So take a few uh, tens of seconds. Okay, so the answer is that it's a random variable, binomial M, binomially distributed with sort of like M is, think of as the population, P is the probability of success. I see, I guess about 40% of you got that. Half of you uh, sort of wrote down M times P. It turns out that that's the average number that get generated, but it's not the actual number. Okay, and the actual number is really random. It depends on the fact that each of them has a probability P of success. Okay, so let's talk about noise. And what I want to do is introduce what's called entanglement distillation. And so let's say that Alice and Bob share three bell pairs, and the bell pairs have a fidelity F naught that's less than 1. What distillation refers to is essentially operations that would be performed on the bell pairs, let's say at each node separately, uh, and followed by measurements of all but one of the bell pairs. Okay. And what distillation will do is it can produce a much higher quality bell pair than any of the three were before. Okay, so with a final fidelity F that's greater than the initial fidelities were. Now, it seems like you get a free lunch, and but we'll look at that in a second. Here is just a very simple protocol that does distillation on two bell pairs. One of them is referred to as the source pair. The other is a target pair. Alice and Bob essentially perform C naughts between the source pair and the target pair. And then each of them measures off their target pair qubit. And they exchange the classical bits that they obtain from that. And what's important to understand is that you can get a strongly entangled pair, but it's probabilistic. You may fail in getting a better, let's say, a higher quality pair. And so it turns out that when you do distillation, then there's some probability that you'll have success. Here I have a graph. Suppose we take as the x-axis the initial fidelity of the two qubits that are using that protocol on the previous slide. And what I'm showing in blue is the final fidelity. And what you see is that let's say in the case where the initial fidelities are 0.7, you can generate a final bell pair with a fidelity of like 0.85. On the other hand, there's some probability that you will fail. And so the red curve here is showing the probability that you actually succeed. And so if the initial fidelities were 0.7, It turns out you will get a bell pair with fidelity 0.85, but only about 60% of the time. And the rest of the time, you get nothing. So that brings us to the fourth poll question, which is, I just want to make sure you understand the purpose of distillation, and look at the choices of, it increases EPR pair generation rate, it increases fidelity, it increases the distance of entanglement distribution, it decreases fidelity of generated EPR pairs, so that you can increase the generation rate, or you're not sure. Okay, so the answer is that it increases fidelity of generated bell pairs, and I see that over 80% of you had that, and it was sort of uniform about the others. I think it's pretty clear that that must be the case. Okay, so I guess that brings me to the end of what I'm going to talk about for now, and I'm going to turn it over to Matheus.
Yeah. Thank you. Thank you,
And
Don.
so I'll stop sharing.
Can you just confirm that you can see my slides?
Yes, see it.
Okay. Yes. And just one quick thing. There may be some poll questions that are slightly different the way they appear in the slides. I'm not sure. Once we're going through them, I think we'll see. But just so that you know, there may be some questions that are a little bit outdated. Okay. So now that Don introduced pretty much this initial background on quantum networks, we're going to talk about scheduling in two-way repeater chains. And the idea is that we want to do entanglement distribution over a chain that has, let's say, n plus one nodes, like we see here in the slide. And what we want to do is to generate entanglement between node 0 and node n. So the question is, how will we generate entanglement between these n nodes? And we're going to break this question into two pieces. The first is when we do link level entanglement generation, and the second is when we perform entanglement swapping. So we need to address both of these to fully answer the question of how you generate end-to-end entanglement over a two-way quantum repeater chain. And there is a very important fundamental behind this, that is the swap operations that we saw before commute with each other in the following sense. Let's suppose that we have this repeater chain here interconnecting nodes A and B. And let's assume that we have generated all link level entangled states that we need to do communication between A and B. It turns out that the Bell state measurements we need to implement entanglement swapping commute with each other, meaning that we can perform any ordering of entanglement swapping and still distribute the same end-to-end entangled state under the assumption that we have no noise. Moreover, we can even perform all entanglement swap operations in parallel at the same time because of the commutability of entanglement swapping. Nonetheless, the order that we decide to do the entanglement swapping operations in each one of these repeaters will have a profound impact in performance and also in the way that we design our quantum network architectures and protocols. Today, we're going to look at three entanglement swapping policies. The first is sequential swapping. The second is swap as soon as possible, or swap ASAP for short. And the third one is nested swap. And throughout this exposition, we're going to assume that the swaps are deterministic and then later on see what happens when we assume that swaps are probabilistic. So let's start with the simplest way that we can do entanglement swapping in a chain, that is sequential swap. Again, we have this repeater chain here interconnecting nodes A and B with three repeaters. And the process will unfold as follows. We're going to start link level entanglement generation at node A. in order to generate entanglement between that node and repeater R0. And that will take some time t sub 0. Whenever we successfully generate entanglement between these two nodes, we can start generating entanglement between R0 and R1, which will take some time t1 because link level entanglement generation is a probabilistic process. Whenever we finish this, we can perform a Bell state measurement in the repeater R0, which is an entanglement swapping operation, and generate entanglement between A and R1, and taking a total time of t0 plus t1. We then repeat this process until we reach a B, or we generate an entangled state between A and B. This goes as follows. We generate link level entanglement between R1 and R2. We'll take some time t2. We perform a Bell state measurement. Then we generate link level entanglement over the last link, which takes time t3. We perform a Bell state measurement. And finally, we generate an end-to-end entanglement between A and B. And the time it takes us to generate this is the sum of the times that it took us to generate link level entanglement for all links. This makes the latency of entanglement generation in this particular swapping rule to be linear in the number of repeaters n. So let's go over a quick poll question now, poll question 5. What is the end-to-end entanglement generation latency when we perform sequential swapping? A is constant, O order of 1. B is linear, O of n. C is quadratic, O of n squared. D is logarithm, O of log n. Or E, you don't know. And let's take some time here. Okay, so most people got it right. The answer is linear, order of n. In the linear in the number of repeaters. So now let's look at a slightly different way of generating end-to-end entanglement, which is swap A SAP. Again, we have the same setup as before, our repeater chain interconnecting nodes A and B. And differently than before, what we're going to do now is that we're going to do link level entanglement generation attempts simultaneously on every link in our chain. And then whenever we have two entangled states reaching the same repeater, we will perform a Bell state measurement. So let's imagine the following happens. We are performing our link level entanglement generation attempt for all links. After some time t0, we generate our first entangled state between repeaters R1 and R2. At this point, we cannot do anything because we only have one entangled state generated between two nodes. Then at time t1, another entangled state is generated, but now between nodes A and R0. At this point, again, we cannot do anything because there at no point in this chain, there is a node that has two entangled states attached to it. And finally, at time t2, we managed to generate an entangled state between nodes R0 and R1. At this point, we can perform two entanglement swapping operations, one at R0 and one at R1. And in fact, in this case, time t2 is greater than t1 and greater than t0. Once we perform our Bell state measurement operations, our result is an entangled state between A and R2. And we keep doing this until we perform a swapping operation on all repeaters, every repeater in the chain. So at this point now, we have generated an entanglement between A and R2, and it took us time t2. At time t3, we generated another entangled state now between R2 and B, and we can finally perform a last Bell state measurement in R2, generating an entangled state now between A and B. Okay, so let's go over a quick poll question now. Sorry, one thing I forgot to say there. The latency to generate end-to-end entanglement here is logarithmic in the number of repeaters n in the chain. So let's go back to our poll question. Which of the swap policies exhibit a lower latency? A, sequential, B, swap A SAP, or C, both are the same. Okay, let's see the results. Yeah, I guess most people said swap A SAP, which is actually the correct answer. Swap A SAP exhibits lower latency. And now let's go to the seventh poll question, that is why. So option A, swap A SAP has latency or on the constant latency, and sequential swap has linear latency. B, swap ASAP has linear latency, and sequential has latency on the order of n to the 3/2 latency. Sequential has linear latency, and swap ASAP has logarithmic latency, letter D, or letter C, sorry, or letter D. Sequential has cubic latency, while swap ASAP has n squared latency. Okay, let's look at the results. So I think, yeah, now we got most people answering the correct answer. The answer is, the reason is because sequential has linear latency and swap ASAP has logarithmic latency with the number of repeaters in the chain. Okay, so now let's look at the last swapping schedule we'll see today, that is nested swaps. And for this case, we're going to look at slightly longer chain consisting of the 2 n nodes with 7 repeaters interconnecting them. So as before, we're still going to attempt to generate link level entanglement for all the links in parallel, meaning simultaneously. But the way we're going to do our swaps is very peculiar. The first thing we're going to do is to find the repeater at the midpoint between A and B. And then whenever we have successfully generated the entanglement between A and that repeater, and between that repeater and B, we will perform a entanglement swapping operation. We're going to repeat this type of division until it's not possible anymore. So let's see how that goes. The repeater at the midpoint is repeater R sub 4. Then we're going to look at another repeater or the other 2 repeaters in the midpoint between A and R4 and between R4 and B, which in this case are repeaters R2 and R6. We can still repeat the sort of division process, reaching these 4 repeaters that we see here with these dotted circles. Now that we specified these 3 classes, we're going to do entanglement swapping first on the dotted circles, then on the dashed circles, and finally on the solid circle. Let's look how this goes. So we first generate link level entanglement for the links. We are performing this process in parallel, remember this. And whenever we have 2 links available, let's say our R1, we can perform a Bell-State measurement here. If we have 2 links touching repeater R3, we can perform link level Bell-State measurement here. What is important to note is that we're not going to perform a measurement, a Bell-State measurement in repeater R2 before we do generate entanglement. We perform our Bell-State measurement in repeaters R1, R3, and it goes as in the same way. So now, once we generate perform a Bell-State measurements in R1 and R3, R5 and R7, we can focus on R2 and R6, repeat the process, generate entanglement now between A, R4, R4, and B, and then finally perform the last entanglement swapping operation to generate entanglement between A and B. Okay, so let's do a quick analysis and compare these 3 types of entanglement swapping scheduling procedures. It turns out they do have different performance. And in fact, if we assume that the swap operations are probabilistic, the K rate, meaning the probability that it successfully generate entanglement between the n nodes, will change drastically for these 3 swapping procedures. Nonetheless, sequential swapping is very simple to implement, as it follows the process that we use in classical networking for communication. Moreover, swap ASAP and nested swaps may require additional control for you to figure it out which Bell states should undergo a Bell state measurement with each other, with other Bell states, so on and so forth. So you do need some sort of additional control when compared to sequential swapping. We can put everything together in this sort of table where we're going to compare just the 3 methods. And it turns out that the probability of scaling with n under the assumption that the swap operation is probabilistic is as follows. We have an exponential decay in the probability generation rate based on the number of repeaters that we have for both sequential and swap ASAP. Although for nested, we have some sub-exponential decay in probability when the Bell state measurement operations are probabilistic. The number of Bell pairs that decohere at the same time is also different for both of these procedures. For sequential, it's always one. There's always one Bell state decohering whenever you're trying to generate link level entanglement throughout the process. But for swap ASAP and nested, we have multiple Bell states decohering at the same time. And that matters a lot because this will influence the quality of your end-to-end state and even which kind of methods you can use to calculate how noise affects the end-to-end entanglement distribution. Finally, the latency, as we saw before, goes as follows. For sequential, is linear with the number of repeaters under the assumption that your probability that the Bell state measurement operation, the entanglement swapping operation, is deterministic and is logarithmic for both ASAP, swap ASAP and nested swaps. Okay, and how does noise play a role here when you're trying to distribute entanglement? Well, let's assume that the entangled states we generate between neighboring nodes are all affected by depolarizing noise, which is a worst case scenario. Let's look at this very simplified setup here where we only have 3 nodes. And let's suppose that we generate link level entanglement in these 2 links here with an initial fidelity of F0 and F1. When we perform a Bell state measurement generating an entangled state between 0 and 2, the fidelity of that state is the product of the individual fidelities for the 2 links we started with. And it turns out that because of the properties of fidelity, the product of these 2 fidelities is smaller than the individual fidelities F0 and F1. When we factor everything into account, it turns out that noise accumulates exponentially in our chain in all cases, even just by assuming that we generate imperfect link level entanglement between neighboring nodes. This means that if you really would like to have some sort of efficient quantum communication happening over large chains, we will need distillation. And not only to determine which types of distillation protocols we're using, we also need to schedule how we're going to feed our link level entangled states and even multi-hop entangled states to distillation protocols so that we can have high quality end-to-end entangled states generated. Again, following the same principles as we saw before, it turns out that different distillation schedules will exhibit very different performance in terms of rate and fidelity that you can achieve in generating entangled states on the repeater chains. We're not going to dive deep here into this topic. It's just for you to know that the decisions that we do, the scheduling that we define for distillation will also have a big impact in that quantum network performance. Okay, so now that we saw the sort of initial concepts for quantum communication, we're gonna dive a little bit deeper into quantum networks. So the idea is that quantum networks will be formed by quantum switches containing quantum memories and that are connected with each other via lossy links. The links will either be used to generate entanglement, implementing a 2-way quantum communication, or to transmit quantum information directly, implementing 1-way quantum communication. The quantum switches will, in 2-way, concatenate link level entanglement that was generated over the links to establish end-to-end communication. And in 1-way, they will decode and encode quantum information so that you can achieve efficient end-to-end quantum communication. And what are the challenges involved when we're discussing or even designing quantum networks? Well, the first thing to do is for sure to try to define whether we're going to perform entanglement distribution, meaning 2-way, or direct quantum state transfer, 1-way. We will need to deal with both loss and noise in order to have efficient end-to-end quantum communication. We will need to decide which user groups should be served at any point in time, utilizing, which leads to problems in performance and resource allocation. And finally, we will need to perform some type of network management so that we can assess how the quality of our network is as we operate it. Finally, it is necessary to also design how data and control will unfold when we are distributing quantum information or generating entanglement. Okay, so now we can shift gears and start looking at one of the second big fundamental topic in this course, that is comparing classical and quantum networks. And the outline for this part is as follows. We're going to see a brief overview on how the internet works. Then we're going to talk about reliable quantum communication, then move to network services and routing. Okay, so let's start with the internet overview. What's the internet after all? It turns out that the internet is a network of networks that is loosely hierarchical, and we have a public internet that interconnects multiple private internets as well. The internet is organized in terms of protocols that will control the sending and receiving of messages. For instance, we have famous protocols such as the Transport Control Protocol, TCP, and the Internet Protocol, for the IP. And the internet is orchestrated or put together through internet standards that are documents called defined in documents called RFCs, requests for comments, which are managed by the Internet Engineering Task Force, IETF. And within this group, there is a group focused on doing research and defining how the internet should evolve, called the IRTF, the Internet Research Task Force. What is very nice about this is that even though we do not have a quantum internet as of today, we already have a group within the Internet Research Task Force that looks that is already thinking about quantum networks, which is the QIRG, the Quantum Internet Research Group, that follows the same principles as the IRTF in terms of requests for comments and trying to define standards that will enable us to create a quantum internet at some point. Let's do a closer look at how the network is structured. We have the network edge that contains applications and hosts, and we can imagine that we live in the network edge. We have the network core that is composed by routers and is in fact a network of networks. And we have access network points where we can access the internet in both wired and wireless forms. The network core is a mesh of interconnected routers, and there's one fundamental question that is addressed here, that is, how actually is the data transfer service implemented through the network? There is essentially two key design principles that are circuit switching, where we have a dedicated circuit establishing communication between two nodes that in a way that resembles how the telephone network works. And we have packet switching, where is a different paradigm where the data that is communicated through the network core is broken into chunks, discrete chunks that are propagated between the routers from source to destination. Okay, so let's dive deeper into circuit switching. Here, the key idea is that whenever we want to do end-to-end communication, we're going to reserve resources to send information. And these resources are the link bandwidth and things like link bandwidth and switch capacity. And because we have we are reserving resources, there is no sharing after a portion of resources were allocated for a particular the communication of a particular pairs of users. What this gives us is this guarantee in performance that is circuit-like. The price that we pay for this is that we need to implement a call setup, meaning we need to transmit some control messages through the network so that we can specify which portions of our resources are being allocated to which user groups or pairs. In packet switching, the idea is to divide end-to-end data streams into packets, and it can be the case that the packets of two users share network resources. It's important to see that each packet in packet switching will utilize the full bandwidth of a link. And what is cool about this is that you can utilize resources only as needed instead of performing allocation or reservation of resources. The key mechanism behind packet switching is called store and forward. And the idea is that we're going to make packets to move one hop at a time. We'll transmit a packet over a link, it will reach a router, and it will be stored in that router until it's time for it to be forwarded to the next router that takes that package towards its destination. This is very interesting, albeit it comes with some issues as well, such as resource contention. It might be the case that the aggregate resource demand that we have in our network may exceed the amount of resource that we have available, leading to problems such as congestions, which means that packets may wait for a long time in the router so that they are forwarded, and which increases latency in communication. We can do a brief comparison between packet switching and circuit switching, and let's look at this particular case here, where we have two routers. We're looking at a link between two routers, and we have three users communicating through that link. Let's suppose that this link has a bandwidth of 2.4 gigabits per second. And the idea is that if we're using circuit switching, we're going to allocate this bandwidth for our three users. In this case, each user will be able to use 800 megabits per second of bandwidth of that link. In packet switching, the idea is different. We are again looking at a single link of bandwidth 2.4 gigabits per second, but now the router has a queue of packets that is being fed by the users. And then whenever this link is available, the router selects one packet in its queue and transmits it through the link. Again, each packet will utilize the whole bandwidth of 2.4 gigabits per second of the link when it is being sent through. We can put everything together and look at a more generic version of this. Again, let's look at the case where we have one link coming out of a switch or router, and that is a 2.4 gigabits per second link. And let's assume this model for communication of our users. Each user communicates 240 megabits per second when it's active, but it's only active at 10% of the time. If we use circuit switching to serve users, and let's imagine that we have 10 users, we can, if we use circuit switching to serve these users, we can only support 10 users simultaneously because each user contributes with 240 megabits per second. But if we have packet switching, the picture is very different. We can calculate the probability that we're going to have multiple users communicating at the same time. And if we have n equals 35, it turns out that the likelihood of having more than 10 users active at the same time is smaller than 4 times 10 to the minus 3. And what we really should take out of this is that by using packet switching, we can allow more users to utilize the network. Okay, so now let's go over a quick poll question here. Poll question 8. In packet switching, A, a connection between endpoints is created before the communication starts. B, users share the bandwidth of channels at every instant. C, the amount of bandwidth available is inversely proportional to the number of active users. Or D, packets use the entire bandwidth of the channel when transmitted. So let's take some time and then see what the correct answer is. Okay, and let's look at the correct answer. The answer is D, which was the most voted answer, that packets use the entire bandwidth of the channel when transmitted. Okay, so let's proceed now. The internet structure is that of a network of networks, which is roughly hierarchical, and it goes something like as follows. At the center of this hierarchy, we have Tier 1 ISPs, such as Verizon and Sprint, that will provide national or international coverage, and they will treat each other as equals. So essentially, tier one providers will interconnect among each other in a privately, and these connections are essentially determined by contracts. Then tier two ISPs are smaller that will pretty much offer regional coverage, and they will connect to one or more tier one ISPs and other tier two ISPs as well. Again, tier two ISPs will pay tier one ISPs for connectivity to the rest of the internet, and tier two ISP is essentially a consumer of a tier one ISP provider. And then we get tier three ISPs that are local ISPs that will act as last hop access networks that will be the closest to the end systems. And they will again connect to tier two ISPs or higher order ISPs to allow them to connect to the rest of the internet. So it turns out that in this network of networks, a packet that is sent from source to destination traverses many networks on its way. And now we reach a very interesting point that is one of the, I would say, most important design principles behind the way that the internet developed. That is the internet protocol stack. The idea is that we would like to break the problem of communication into layers that will provide abstractions, and it will allow us to solve well-defined problems that, when composed, allow us to implement communication efficiently. So the layers that we have in our protocol stack are the application layer, the transport layer, the network layer, the link layer, and the physical layer. And they work as follows. So essentially, the one layer utilizes the layer below it as a service to accomplish its own duties. So the application supports network applications, as we have, for instance, web browsing or email, and these are just protocols here that implement this type of services for us. The transport layer will deal with host-to-host data transfer or end-to-end data transfer, and the two key protocols in the transport layer are the TCP, Transport Control Protocol, and the UDP protocol. We have the network layer that deals with routing of packets from source to destination, and perhaps it contains the most well-known protocol in the internet, the Internet Protocol, which names the internet, the IP, that operates on top of the link layer that deals with data transfer between neighboring network elements. And a very famous example of protocol here is the Ethernet protocol. Then finally, the link layer operates on top of the physical layer that deals with how bits are propagated on wires with electromagnetic waves. Well, in the same way that this helped us to define the internet, it may be the case that this will help us to design the quantum internet, and we already have ideas for how to come up with a quantum internet protocol stack following the classical internet protocol stack. This is not a set in stone idea. This is not a standard yet, but there are a lot of research being done on how we should actually define the internet, the protocol stack for the quantum internet. So the stack that we're going to see today here mirrors exactly the stack that I showed before. It has 5 layers: application, transport, network, link, and physical layer. And each layer will do as follows. So application will support quantum network applications, such as, let's say, quantum key distribution. The transport application, a layer, will deal with host-to-host quantum data transfer. And you can imagine the quantum versions of the transfer protocols we saw for classical, such as the QTCP and QUDP. Then the quantum transfer layer will work on top of the network layer that will deal with entanglement generation between end nodes. And maybe you'll see the quantum internet protocol, the QIP, to be defined in order to allow the quantum network layer to operate. This layer operates on top of the quantum link layer, which deals with link level entanglement generation. And finally, the physical layer that deals with photons traversing wires in order to generate link level entanglement, for instance. Okay, And now uh, I think we got to the point where I'm gonna give the baton to Don again.
Right, right. So
So
I
let me
think
just.
why don't we take a 10-minute break now?
I think that's a good idea.
Actually, maybe the thing to do, I'm looking at my watch, it's what, about 4:18. Let's just start up at 4:30 Eastern time. I guess that's
Hmm.
about 12 minutes. Okay.
Yeah, that sounds great. Okay.
Okay. Welcome back. Um, so I'm going to do the next section. I want to cover some more topics with respect to classical versus quantum networks. Um, it's interesting to look at how classical networks provides for reliable communications and contrast that with what we expect will be the case with a quantum network. So let's start with the reliable classical communications. First of all, it's important to know or understand what kind of error models uh, the classical network has to deal with. Um, they consist of, let's say, that you could have bit flips, you could have bit erasures, and it's worth noting that for in almost all classical channels, these occur with very, very, very low probability. In a fiber optic channel, a bit flip might be on the order of 10 to the minus 9. Uh, there's another error that occurs in classical networks, namely, since it incorporates packet switching, and you have packets that are being sort of transmitted between routers and between nodes. The routers, as Matheus pointed out, can have queue buildups where you have lots of packets are coming in at a higher rate than the router can actually deliver to the next node. And it's possible for the memory that the packets are being stored in to fill up. And then another kind of error is that you can have a packet dropped. And that years ago was very common. It's much less so in the current internet, but it does happen in sort of specialized networks. Now, the way that the classical internet deals with this is by using error detection and error correction codes. And in the case of drop packets, it will retransmit packets. And the way that that would work is the source has a packet, let's say Alice is sending to Bob. Alice will make a copy of that packet, transmit one of them into the network, and it will pass through to Bob. And what it relies on then is on cloning, which, it's important to understand that that's not really possible in a quantum network. Here on the right, I have sort of a schematic of a very, very simple packet retransmission protocol. We have a sender, we have a receiver. The sender sends a packet, let's say packet 0, it's received, and the receiver sends an acknowledgement back to the sender. And once the sender receives the acknowledgement, it sends the next packet, packet 1. And let's say it gets lost, it gets dropped. Uh, so how does the sender handle that? Well, every time it transmits a packet, it sets a timer. And if the timer goes off, times out, then it interprets that to mean that uh, the packet it sent was lost, and therefore it never received an acknowledgement back. And so then it would resend the packet, makes it to the receiver would send the ACK, the sender would then send the next packet. In this particular algorithm or protocol, it turns out that it works where you just give ID of 0 or 1 to the packet. So you're either dealing with packet 0 or you're dealing with packet 1. And this is just a very simple example of a packet retransmission protocol. The internet uses more complicated versions of this. So what is it that changes in quantum? And just to before we look at what happens there, it's important to remind ourselves what can happen in quantum communication. And one is that we can have, let's say, the loss of qubits due to loss of photons. The other is that the qubits can be corrupted by noise. Okay, and so both of those have to be handled. And so when we think of errors, then there are all sorts of sources for errors. And I should mention that there's been a lot of work on modeling errors in quantum systems. There's this idea of a Pauli channel that essentially introduces errors that correspond to Pauli operations. You can have erasures, namely a photonic qubit just gets lost. You can have amplitude damping, and that can be used to sort of model certain kinds of decoherence. You can have noise introduced through gates, memory decoherence. In many of these quantum communication systems, you find that the memory qubits, when you want to essentially transfer to a photon, they operate at sort of a particular natural wavelengths. Okay, but the wavelengths, in fact, a very common one is that a wavelength of like 800 nanometers. The problem is that telecom fiber optical systems have been designed for photons at 1550 nanometers. And so then you have to do some kind of conversion, or what's referred to as transduction, and that will introduce loss and noise. You have optical components at these various subsystems that introduce loss. You have to detect photons, and there are inefficiencies there. Matheus indicated that there are systems where swaps are probabilistic, and so that has to be sort of modeled as some kind of a loss. Okay, and so you can think of it that error models are much richer in the quantum domain. It means also that recovery schemes are sort of like a much broader variety. There's quantum error correction, which is used especially for one-way communication. We've talked about distillation as a way of sort of increasing the quality of a bell pair. You could think of doing data retransmission in a one-way scheme, but because you can't clone quantum state, the only way you can do that is the source would have to regenerate the same state for a retransmission. In the case of a two-way scheme, you have this nice property that bell pairs are fungible. You don't really care what bell pair you get. You can use any one. And so in that case, you can just attempt generating bell pairs until you succeed, until you get it from Alice to Bob. So now what I'd like to talk about is look at the network layer in the quantum network according to the protocol stack that Matheus introduced. and talk about the kind of service models that one would might think of. So first of all, let's review what the functions of the network layer are in a classical network. Namely, it's to transport a packet from, let's say, a sending host to a receiving host. Okay. And what that means is every host and every router has to have all of the network layer protocols that sort of participate in this transfer between two end nodes. And so there are three important functions of this network layer. One, we need to select a path or a route between the two end nodes that the packets would be taking. And that's usually done with the assistance of some sort of a routing algorithm. Uh, Second is you have these routers and they're connected to multiple interfaces, multiple links. And so we need to uh, move packets from, let's say, a router's input to the appropriate router output. And you can think of that as the switching function of the router. And then some network architectures require a router call setup along a path before you actually send data along. Turns out that's the case, let's say, with a protocol like TCP. Okay, so the crucial question is what kind of service model are we going to have for the channel? Think of it as this abstract uh, uh, object that transports protocols from the sender to the receiver. Okay, should it guarantee bandwidth? Uh, should this service be concerned with, let's say, the timing between packets? Let's say try to preserve interpacket timing. Should it guarantee reliable delivery of packets? Should it guarantee that the packets are delivered in the order that they were put into the network? What kind of feedback should be provided to the sender, let's say, associated with, let's say, congestion or problems within the network? So this is really the most important abstraction that's provided by the network layer. And in the classical network, it really comes down to either providing a virtual circuit service or a datagram service. So I'm going to talk about each of these in turn. So let's start with a virtual circuit. You can think of it as the following. We have a packet switch network, but what we want is that the source to destination path behaves in some way like a telephone circuit, as if it would look almost as if you were doing circuit switching. And this would be, we would expect this performance-wise and in terms of kinds of actions that the network would provide along the source destination path. Okay, in order to provide virtual circuits, you would need to be able to perform call setup and tear down for each call before the data can flow. You would associate a virtual circuit identifier with, let's say, this particular uh, call, and each packet then would carry that VC identifier. And it's important to understand that that would not be the same as, let's say, the destination host address. Okay. Every router on the source destination path then would have to maintain state for each passing connection. And we would or we might have to allocate resources on each link and each router on the path to the virtual circuit. And that would be like bandwidth and memory, if we wanted to guarantee some kind of circuit-like performance. So here is how we might expect it to look in practice. We have two end hosts connected by a network. We're looking at the network layer in red. And the first thing we would do is we would initiate a call. The destination would get this request to initiate a call. It would accept the call, and then that acceptance notice would go back through the network and be received by the sender. And then the sender could start sending data, and the receiver could receive data. And so that's sort of how it would look like. Of course, there are nitty-gritty details as to exactly how you would do that. The other service is what's referred to as a datagram service, and this is what the classical internet actually offers. It does not offer this virtual circuit service. And in the datagram network, there's no call setup at the network layer. The routers do not store any end-to-end connection state. They have no idea what the packets that traverse them, what they're doing. All that they're worried about is deciding what output interface to put them on. And there's no network level concept of a connection. The packets are typically routed using the destination host address. And that's the way it's done in the internet. And it's possible that because there's no connection state anywhere in the network, packets between the same source destination pair may take different paths. And so here's a schematic of what we might expect. So the network would just send data, no call setup, and could go over different paths, and the receiver would just receive the data. So that brings up the question, that's what we do in the classical internet. So what kind of service model ought we to be thinking about in a quantum network? Okay. What service model should the quantum channel between the end nodes provide? Should it provide a guaranteed rate, some sort of latency guarantee? One thing different between quantum and classical is that the quantum information can suffer from noise. So should the service provide a minimum fidelity guarantee? And so this is really the most important abstraction that would be provided by a quantum network layer. And it turns out in the context of quantum networks, here the choice is between are you going to provide an entanglement generation service where you're just generating and distributing entanglement between pairs of end nodes, or are you going to provide a service where you're essentially transferring quantum information from a sender to a receiver? And so those are the two sort of most, let's say, important services to consider in the quantum network. And so just to remind you, if we were going to do entanglement distribution, basically, we're creating and distributing bell pairs, and we would the network would sort of be creating them, let's say at the link level, using the nodes to do bell state measurements to propagate the bell pairs to the end nodes. And it turns out that if you have a network that provides this service, but really what you want to do is to transfer quantum information, that's easy. You would just use teleportation to do that. The network would be generating these bell pairs, and then you would just teleport quantum state from one node to another. And this then would rely heavily on distillation. It would rely heavily on multiplexing to handle loss plus noise. And as we saw earlier, of course, it's going to require the exchange of some classical information for correction. Okay, so this brings us to a poll question. And the poll question is really, what's the purpose of quantum teleportation? Is it for error correction when you distributed bell states? Or is it do you use it to transport classical information from one user to another by, let's say, using a bell state as a resource? Or are you using to transport quantum information from one user to another by the expenditure of a bell state? Or do you use this to transport humans from spaceships to planets? Okay, so the answer is that you use it to transport quantum information from one user to another, and you use a bell pair. And I see that almost all of you got that right. A few of you answered that you use it to transport classical information. That's not the case, although it's very interesting that there is a different protocol that is useful for transporting classical information with bell pairs as resources. But teleportation really is you're teleporting the quantum state from one node to another. And then, the other service that I mentioned would be a quantum information transfer service. And so that would correspond to a one-way network architecture. And basically, you would just transfer quantum information directly. Uh, it's, it's interesting to note that that looks a lot like the classical internet. Except that instead of, let's say, transmitting packets from a sender to a destination, here you're transmitting quantum information from a sender to a destination. And so you would expect that you could borrow a lot from the classical internet to sort of build protocols for this. As I've indicated early on, in order to do this, to transmit one single logical qubit, you need to use quantum error correction. And so you might need tens or even hundreds of physical qubits in order to be able to be successful. And one thing about this is you don't require the exchange of classical information. That's an advantage of this one-way network architecture. It's important to note that the two services are interchangeable. If you have a network that transfers quantum information, you can use it to distribute bell pairs. And the way that you would do that is that in the example that we had here, this node here could generate a bell pair and then transfer one of the qubits over to the destination while keeping the other qubit, and then they would share a bell pair. So they're both interchangeable. So if we look at one-way versus two-way, with two-way pros, it turns out that, although we're not going to go into this, distillation is simpler than quantum error correction. Bell pairs are fungible. And the benefit of that is that, as I said before, you don't care what bell pair you use. And so you can get high rates and you can sort of pre-share entanglement before you need it if you need. And it turns out that it's tolerates noisy gates better than one way because it's not using error correction, it requires many fewer gates, and so the noise is less of a consideration. The con is you get increased latency because you have to do this exchange of classical communications. And as we saw, the repeaters need to have quantum memory, and so potentially there could be a high memory requirement. If we look at the one-way, on the positive side, no classical comms, which suggests that you can have low latency. You're not storing things at the repeaters, storing quantum state at the repeaters, so the memory requirements are lower. And it, what you can do is you can use this to sort of pre-share entanglement before, let's say, some application needs to use it, let's say for distributed computing. On the downside, quantum error correction is very challenging and active area of research, requires high quality gates. And as I've alluded to previously, you need a lot of physical qubits to correct a single logical qubit. And studies suggest that you would need many more repeaters when you're doing one-way than if you're doing two-way. Okay, so that brings us to poll question 10. And so here it's, what are the advantages of a two-way quantum network architecture? And you can select all that you want. It tolerates noisy gates. It introduces latencies because of the need for classical communications. It requires considerable quantum memory at switches. It can provide high rates, or you're not sure.
Sorry, Don, as they answered this, just in this case, for instance, we have a slightly different wording for the poll question, but the idea is pretty much the same. Just so people know, the poll questions they are seeing on Zoom has a slightly different wording.
Oh, I see. That's what you were referring to.
Yeah.
So it turns out that A and D are sort of like advantages of two-way. It's more tolerant of noisy gates, and because things are sort of simpler and bell pairs are fungible, it can provide high rates. And I see that those are the two that were most chosen. The other two, unfortunately, the poll question wasn't really listed well, that the one where you put the answers, but these two are sort of like cons or downsides of two-way communication. Okay, so that brings us, so quantum internet, Matheus sort of showed you what it would look like for the classical internet. And so you can think of it, the expectation is it's going to be similar, that as the quantum internet gets rolled out, it's going to be rolled out in terms of like lots of small networks that will end up being connected to each other. And what we expect is that the quantum information is going to pass through many networks. And if you're doing end-to-end entanglement, it's going to be over many networks. And We are likely to find that, one network might use a particular technology called color centers. Another might use trapped ion technologies. Uh, you may have some networks that actually provide an entanglement distribution service, whereas others might provide a quantum information transfer service. But because we know they're interchangeable, we know that we should be able to connect these networks together to provide seamless service to applications and users. Okay, I'm going to look at one more topic, and again, to sort of compare between classical and quantum, and then I'm going to turn it over to Matheus. And namely, I'd like to talk a little bit about routing. So the routing problem is the following. You have a network represented by, let's say, a graph where the nodes in blue are, let's say, vertices, and the lines in blue connecting the nodes are edges connecting the nodes in the graph. And really what we want is we want to be able to find paths between pairs of nodes. And so let's just look at what's done classically. The goal of a routing protocol is to determine a good path, which you can think of as a sequence of routers through a network from destination or from source to destination. So if we take like A here as a source and F here, then it would be, finding some path here that is good in some. Now, what do we mean by good? Well, as I indicated in the previous slide, we have sort of a graph abstraction that we can use, where the graph nodes are routers and the graph edges are physical links, and associated with each of the links is a cost. The link cost could be the delay, the time it takes for a packet to traverse, could be, let's say, a dollar cost of some sort, an economic cost, could be some level of congestion. And a good path then typically means a minimum cost path. And there are other definitions possible, but that's sort of the standard definition for a good path in the classical internet. And we know that there are very efficient algorithms for finding minimum cost paths. Dijkstra's algorithm, of course, being sort of the canonical one. And here I'm showing the minimum cost path between A and F. Okay, so routing algorithms sort of come in different classes. You could classify them as either being global and collecting all information about the network at one place, and then running an algorithm to find good paths, or that it's decentralized. Okay. And as I said, global, you'd have a central controller. It has complete topology, link cost information. Decentralized, the routers might know their physically connected neighbors and what the link costs are to those neighbors. And then all the routers would perform sort of an iterative computation where after each iteration, they would exchange information with their neighbors that would then feed into the next iteration. And this is exemplified by what are called distance vector algorithms. Another way of classifying, are they static or dynamic? And by static, that you would compute the routes and you wouldn't change them for a long period of time. Perhaps you would instantiate them for a day, and then you might recompute the routes again for the next day. And by dynamic, the routes would change more quickly, and you would perhaps would be doing periodic updates. It might be on the order of minutes or seconds, or it could be that you do updates as you observe that link costs change. The current approach in the classical internet is to do everything centrally, where you have complete topology and complete link cost information. I preface it with logical because some networks are so large that you can't really quite do it at one place, and there might be some benefit in having it, let's say, 2 or 3 nodes doing the computation. One thing that does show up in the classical internet is that internet service providers, network administrators may have policies regarding how their networks can be used. And so they have to, the computations have to account for these policy constraints. For example, party A might not be allowed to use a particular set of links in party B's network. All the route calculations include calculation of backup paths so that if a link fails, the network can very quickly reconfigure and using the backup paths. And then you want to avoid the possibility that a link could be a bottleneck. And so most routing algorithms try to take advantage of path diversity for load balancing to avoid bottlenecks. And then what you'll have at router R naught, the result of this then will be sort of a routing table. And it could be that, if the destination address is A, then, you send packets destined to A to neighbor R1. If it's destined to B, you send it to R2. That's how the algorithm or the routes would be instantiated. And it turns out there's been a lot of work done on routing in quantum networks, and most of it sort of follows along the lines of what I've described here, with really the difference being, if I go back to the previous slide, the difference being what this link cost looks like in a quantum network. And many of the proposed algorithms try to account for fidelity as part of the link cost. Okay, so let's look more closely at a two-way net. In order to generate, let's say, a bell pair between 2 destinations, we need to generate a path of links, and we need to generate the bell pairs across each of those links. Okay, and we know that link level entanglement generation is probabilistic. And so that brings up the question of how to perform routing. Okay, so we have A and B. They want to generate entanglement. A controller could find a path P, which I've, let's say, indicated here in red. And then once you have the path, you could distribute entanglement using any of the 3 scheduling policies that Matheus introduced a while ago. And you could just repeat until you get successful generation of entanglement. So these methods work, although, there's a question about how much time is required to do this. There's a question also as you scale the network up, how will the hardware requirements scale? How much memory will you need? And so on and so forth. When you do something like this, it's tantalizing to ask the question of, well, do you do something like circuit switching, where maybe you sort of provide a subset of wavelengths to one, let's say, user pair, and a different set of wavelengths to a different user pair, and just dedicate them? Or can you do something like packet switching? And Matheus will be talking about an approach that looks a lot like packet switching shortly. Okay, so let's just do a quick back of the envelope analysis. And we're going to assume the two-phase time-slotted model for link level entanglement generation and for swaps. As I mentioned before, if memories only last, let's assume that qubits, when they're stored in memory, they have to be used immediately. And in that case, then rates decay exponentially with distance. If you have probabilistic swaps, then in order to generate non-exponential decay, you need special treatment, like doing something like nested swapping. And exactly the kind of performance you're going to get is going to depend on whether you're doing multiplexing, how much multiplexing, what the coherence times are, the attempt frequency. And it's important to note that in the classical, time scales linearly with distance, and the rate is constant. But it's not clear that we can do that in the quantum world. And so let's just sort of take a look at that. And we're going to consider a very different paradigm from what I showed you before, and going to sort of illustrate it in a very simple two-dimensional grid network, okay, where the nodes are connected, as you see here. You could think of this as sort of looking a little bit like the Manhattan Street system. And suppose we have Alice at this node and Bob here, and they want to generate entanglement between them. Suppose P is the probability of successful generation of a bell pair across a link, and let's just assume it's the same for all the links. Okay, and we're going to assume time is slotted, and that each slot would allow generation of link level entanglement, and when it succeeds, you can also do a swap during that time slot. And that you just continue every time slot attempting to generate link level entanglement. Okay, and that you can only store one qubit per link per router, and you have to use it or you lose it before the next time slot. And let's suppose that swaps are probabilistic and they succeed with a probability Q. And I already stated this assumption. Memory is only good for one time slot. And now what we're going to do is we're going to allow routing across multiple paths. And so let's look at sort of an example. Here we have Alice, and let's suppose that we attempted to generate link level entanglement, and where there are edges between nodes, it succeeded during that time slot. And the ones I've colored green uh, correspond to paths between Alice and Bob. And so in this particular time slot, we succeeded in generating two paths between Alice and Bob. Okay. And so then before the time slot would end, we would then do swaps with success probability Q on all of these nodes between Alice and Bob. And so the success probability for each of these paths then in terms of the link level entanglement is just going to be the probabilities of success across each of the links. And for, let's say, path L, it's going to be proportional to the probability that you successfully swap at all of the nodes on that path. So the P sub L will be proportional to Q to the power that's the number of links on that path. Okay, in order to do that, you require global knowledge. Okay, and you require it immediately in order to do it. Okay, it turns out that there are suboptimal algorithms that can get by just using local information. Okay, and so what I'd like to do is to sort of give you a sense of sort of kind of results. There's a sort of an area of physics that's referred to as percolation theory that turns out to be very useful in sort of understanding how these networks and these kinds of algorithms would work. Okay, and I'm not going to go into it, but what I want to point out is the following. Let's look at this three-dimensional graph here. And what we're doing is we're looking at an Alice-Bob pair, and we're looking at the distance between them on the x-axis here, and on the y-axis on this axis right here. And then what we're plotting is the logarithm of the entanglement rate that they are able to generate. So you can think of as x gets larger, y gets larger, Alice and Bob are getting farther and farther apart. And what we find is the following. Take the probability of successfully generating entanglement across a link to be 0.55, and the swap success probability to be 1. Then what you see is the rate you get is flat. It doesn't depend on the distance between Alice and Bob. If you reduce the link level success rate for entanglement to 0.45, then things change. All of a sudden now what we see is an exponential decay in the rate. But what this tells us is that because we are allowed to sort of use multiple paths, we're actually able to achieve sort of a distance-independent rate, which we didn't see with sort of linear change of repeaters. This graph here, it's the same thing, except now we're making swaps probabilistic. The probability of successful swap is 0.9. And what happens in that case is we see that there's always a decay as the Alice and Bob get farther and farther apart. And it becomes more pronounced depending on the kind of algorithm that we use. R sub G is if you find the global optimum. There are algorithms that use local information, and that corresponds to R low. And then if you were only use one path between Alice and Bob, that's this bottom surface here. Okay, so then a question comes up whether you can get distance independent rate even if you have probabilistic swaps. Okay, poll question 11. What's the dependence between distribution rate and distance when swaps are deterministic and the link level success probability is larger than, let's say, some threshold? Do you get exponential decay in a rate? Do you get a logarithmic decay, polynomial decay, or do you get a distance independent decay? Or do you not know? Okay, so we had a range of answers. Almost half of you had the right answer, which is that if P is large enough and above a certain threshold, you do get distance independence, which is nice. Okay. I want to say one more thing about routing, but to do that, what I want to do is to sort of refresh your memory. I talked about GHZ states. An n-qubit GHZ state sort of generalizes a Bell pair, and what would ordinarily be a Bell state measurement or entanglement swapping becomes a more complicated operation that's called a GHZ fusion. And so you might have, let's say, 3 GHZ states shown here, where one qubit from each of those is in one place, and then you can do a fusion operation on it that will generate a larger state, or if it fails, you'll just end up with a 1,3 GHZ state and a bunch of Bell pairs. So it turns out that you can use routing with GHZ in the following way. Suppose that you generate link level Bell pairs, which I show as these black edges between the nodes. And what you do is if you have 2 incident edges at a node, you perform a Bell state measurement. That's what's in green. But if you have 3, you do a fusion operation. Okay. And it turns out that when you do that, if all of the nodes, let's say, perform these GHZ fusions, you get something that looks a lot like broadcast, like from Alice to Bob. And if P and Q are sufficiently large, you get percolation, and percolation comes with it that you get a distance independent rate. And unlike the approach that I showed you before, you actually get distance independent rate even if your sort of fusion probability, or think of it, your generalized Bell state measurement probability for success is less than 1. And so this sort of allows you to get distance independent with probabilistic generation and with probabilistic swaps. And you can sort of design different protocols depending exactly on how you sort of perform these fusions. That's something I'm not going to get into. Okay, so to summarize this, so entanglement distribution is very different from quantum information transfer. Um, and that because of that, you get these sort of new problems that don't show up in classical networks. And even like old problems like routing, have sort of extra wrinkles like, okay, you have to worry about fidelity. Okay, and so it's sort of a very exciting area because you have to worry about resource allocation, path selection, you got worry about how you would deliver quality of service. Okay, and I'm going to stop here and pass it on to Matheus.
Yeah. Okay. So I think actually we can cover quickly router and switch architecture, and then move to discussing a connectionless two-way quantum network architecture. So let's do that. Let's start by looking quickly on an overview on classical routing architectures. There are essentially two key functions in a router. That is that the router should run routing algorithms or protocols, and it should implement forwarding of packets from incoming links to outgoing links. And the idea is that the router is composed by a high-speed switching fabric that will allow us to send packets from input ports to output ports. The routing has a processor that will run the routing algorithms and protocols and decide what it should be done with the packets in the incoming queues. Okay, so there are interesting questions to ask here. That is, for instance, what is the capacity of a router? Can we come up with scheduling policies that will tell us how we should actually switch packets from input ports to output ports that will achieve the communication capacity of the router? Can we do that by also minimizing the complexity of the switching fabric? And we answer those questions by looking at matching algorithms that will, again, match input to output ports, look at max wait policies for scheduling, and also we can even follow lightweight randomized algorithms that will allow us to serve our packets with a reasonable overhead. Okay, so this maps a little bit to the two-way quantum switch, which is a slightly modification when compared to a repeater. It has a slightly different modification. That is, it can interconnect multiple users and not only two. So again, let's assume here that we have quantum memories that allow us to do loading and readout of qubits of quantum information. Let's suppose that we have access to multi-qubit quantum measurements, such as GHZ fusions or Towsley measurements. These are multi-qubit quantum measurements. We have some quantum logic operations we can perform within the routers, the quantum switches that target maybe multiple qubits and stored in quantum memories. These switches can have access to multi-photon entanglement sources. They can generate photonic states of multiple photons. And also, we're going to require those quantum switches to have access to classical processing and communication hardware. So, okay, in this setup, how would a two-way quantum switch operate? Well, the idea is that we have users interconnected through the switch, generating link-level entanglement with the switch, and we perform Bell state measurements to do to generate end-to-end or user-to-user entangled states, consuming the link-level entangled states. So we can imagine also this type of two-phase communication approach, where in phase one, we generate link-level entanglement in a random way because the process is probabilistic inherently. And in phase two, given the outstanding requests that we have, which users we should connect together, the switch can select which Bell pairs to perform BSMs or even GHZ fusions so that we generate the necessary end-to-end entanglement. And this idea of selecting which users to serve actually maps to selecting an eligible matching in the graph of the memories. So here we can use an abstraction where the qubits, the memories that we have in the quantum switch, are nodes of a graph. And what we want to do is to perform a matching between these qubits. So each edge in this matching would represent a Bell state measurement, for instance, to be performed within the switch so that an end-to-end entangled state is generated. Okay, and there are many challenges here. For instance, you need to determine the switch design and the switching fabric. Would you have this type of teleportation fabric, or how can you implement your Bell state measurements? Do you have an all-to-all connectivity, meaning you can perform a Bell state measurement between any two qubits on your quantum switch, or do you have some type of constraints regarding which qubits can be you can undergo a Bell state measurement together? You should also there's also interesting questions on determining what is the capacity of a quantum switch and transferring that to the capacity or extrapolating that to the capacity of a quantum network, and how you do network resource allocation in that case. Can you assume that you have some type of global versus, or you could look at ideas that do your switching decisions based on global information or on local information, or even assuming no state information regarding entangled states that are outside of the scope of the quantum switch. Moreover, you can think that now you can have memories that are very good and they can store qubits for longer than one time step, and therefore you might want to utilize entangled states that have different age in order to perform your switching decisions. Again, how would we come up with ways to do switching that takes into account memory decoherence and gate errors? Will that somehow change the type of scheduling policies that optimize switching in the classical problem? Moreover, you should also deal with the quality of the information that you have at hand in terms of, let's say, the fidelity of the Bell states you have stored, noting that because quantum memories are imperfect, the fidelity of our states degrade over time. So in this case, you might want to try to answer questions such as, can we come up with virtual circuit switching ideas to deal with, let's say, this problems in network capacity and resource allocation? And also, should we do some type of decision of which entangled states to use when serving end-to-end requests based on the age or the time that these entangled states have been stored in the switch? Let's say using things like a youngest qubit first queue approach to distribute end-to-end entanglement. All right, and now I guess after this, we are ready to discuss a connectionless architecture for two-way quantum networks. Well, connectionless quantum network architectures or quantum network architecture would relate to an architecture that requires pretty much little or no flow state at the quantum switches and quantum repeaters. Essentially, you might have the case that each entanglement request, the request for generating end-to-end entanglement, can potentially be handled separately by the network, even if that request comes from the same end-to-end pair of users. And then when we look at two-way architectures, we need entanglement swapping, and we can look at the swapping policies that I showed you before. And in this case, swap ASAP and nested swapping would require additional control to synchronize what it's going, how you would essentially swap the link level entangled states together. That would pretty much require some state of connection to be maintained by the quantum routers. And here, sequential swapping really comes at hand because, as we saw before, sequential swapping requires pretty much no additional resource or control over the process, meaning you require pretty much no flow information to be stored in the switches and repeaters naturally. And the only thing you really need to synchronize is link level entanglement generation. So what we're going to see now is how we come up with this connectionless two-way quantum network architecture that is analogous to the datagram service implemented in the classical internet. And what are the pros here? Well, we do have a simplified synchronization approach because we do, in a connectionless architecture, we do communications on a link-by-link basis. It is very amenable to analytics because we know how to understand the systems. We've been studying them and implementing them for a while now. It's easy to understand and very easy to manage compared to more complicated approaches. It also allows deploying classical internet protocols that have also been developed for a while now, such as coming up with a quantum version for the transport control protocol, QTCP, allows us to do destination-based routing in the same way that we use IP in the classical internet. We can even use a protocol like multicast that deals with multi-user communication in quantum by defining multipartite state distribution among user groups. Okay, so let's look at a classical connection architecture again, just to recap what we saw previously. We have packet switching that is implemented using store and forward. We have our TCP/IP network stack that is composed by 5 layers and that help us implement end-to-end communication efficiently. We do, in the network layer, statistical multiplexing that enables us to serve multiple users simultaneously. And this really means packet switching. In packet switching, if you recall, we did that. We saw that brief calculation that tells us that with packet switching, you allow more users to communicate through the network when compared to circuit switching. And this sort of connectionless principle was really fundamental for internet performance, allowing us to have the global connectivity that we reach today, and that in principle we hope to have whenever the quantum internet is around. Okay, so in a quantum connectionless architecture, we're gonna look at essentially 4 layers, and they will also mirror the classical stack that we saw previously, and we also saw this type of quantum stack before, right after we talk about the classical stack. And the idea here is that we're going to have a transport layer that will deal with the flow of end-to-end bell pairs, and we're going to define here the quantum version of the TCP, QTCP. For the network layer, we're going to do routing and sequential swapping with something like a store and forward mechanism. For the link layer, we're going to do heralded link level entanglement generation utilizing a device called the link controller that will essentially determine how to generate link level entanglement. And finally, in the physical layer, we have all types of quantum operations that we need to really do this with the physical qubits that we have. Okay, so let's see how the link layer goes. Again, the idea is to do heralded link level entanglement generation, in principle multiplexed heralded link level entanglement generation. And the idea is the service goes as follows. The nodes request entanglement generation to the link controller, and the controller will orchestrate this generation by determining how many proceed until success or repeat until success to generate link level entangled states between the nodes. So it might be the case that we might need multiple attempts, and all these attempts are controlled by the link controller. And then whenever we do have a link level entangled state, we assign that link level entangled state to the nodes by determining a request ID and a link level label. The request ID will essentially tell the nodes that that request is served by the link level entangled state that the link controller just generated. What is nice about this is that you can easily accommodate link level purification with this link controller model. Finally, what the link layer is doing is generating entangled links for the network layer to consume. And the network layer, we're going to define the quantum datagram. That is similar to the classical datagram idea, but it will contain both classical data and quantum data. And what it will allow us to do is to forward Bell states like we forward packets in the classical internet utilizing sequential entanglement swapping. So let's look at this process briefly. So let's imagine that we have a request for a datagram to be sent over that network here of 4 nodes, and we prepare our quantum datagram in that blue node. After we perform link level entanglement generation, right, we can send that the datagram, quantum datagram progresses 1 hop. Then after some time generating link level entanglement between these 2 nodes, we can perform a Bell state measurement and push the quantum datagram to really go to the next hop. So the idea is that after this, we essentially moved quantum information 1 hop after performing a Bell state measurement. Then we can keep repeating this sort of sequential procedure until we generate entangled state between the end nodes. And here again, what the quantum datagram is doing is allowing us to utilize the store and forward mechanism of the internet following sequential entanglement swapping. What is nice about this is that we have no resource reservation, because in the datagram servers, there's no such a thing. There's no call setup. You just utilize the resources as you need them. We also specify here that the service the network layer will provide is a best effort service. If something bad happens, what you do is that you try to regenerate end-to-end entanglement starting from the beginning. Also, it supports different schedules for link level entanglement consumption here, because the nodes, the quantum routers are allowed to utilize the entangled states that they have generated in any way they would like. So for instance, they could do youngest qubits first or oldest qubit first approach to utilize the entangled states that are stored in memory. And then we get to the transport layer that is essentially the quantum TCP protocol. So the idea is to have a TCP-like opening handshake, followed by a data flow, the generation of multiple end-to-end entangled states between end nodes, followed by a closing handshake that tells the 2 end nodes the generation of multiple link level entangled states has completed. We're going to use acknowledgement messages X for the delivered quantum datagrams so that we can implement the reliable mechanism that Don showed to you previously when we were talking about reliable quantum communications and classical communications as well. Then we can also utilize this to control the end-to-end quantum datagram rate that is being pursued by the 2 end nodes, so that we can do congestion control in the network, following the same type of controller that is used by classical TCP, that is the additive increase, multiplicative decrease approach. What is nice about this is that, as I said before, we can really utilize multiple ideas that were investigated for classical here, such as active queue management, to reduce the issues that we have of decoherence impacting the end-to-end communication. And QTCP is essentially this. It is inspired by, driven by the classical TCP approach. So what we see here now is a graph that shows us the comparison between the quantum TCP protocol and another protocol that does not follow the sort of connectionless principle. And what we see, the graph that we see here is the fidelity by the flow, the index of the flows that are being served by the protocols, these transport protocols. so what we see here is that QTCP is able to maintain many more flows with higher fidelity than the other protocol that does not follow a connectionless principle. Okay, so let's go to our poll question 12. What are the benefits of a connectionless quantum network architecture? A, it requires minimal synchronization. B, it reduces the total amount of required classical communication. C, permits borrowing ideas from classical internet for applications in quantum internet. Or D, provides distance-independent entanglement rates. Or E, I don't know. So let's wait a little while for you to answer, and we'll proceed. I think we have most people getting the two correct answers. That is, it requires minimal synchronization, and it permits borrowing ideas from classical internet to apply to the quantum internet. It really does not provide distance independent rate. It's not enforced in the architecture. You may be able to achieve this by requiring additional ideas, but it is really not something that the architecture provides to you, right? And it does reduce the amount of required classical communication, but really the minimal, when we compare that with utilizing, let's say, a swap ASAP approach or nested swap scheduling, we really do minimize the synchronization that we need. We only do synchronization for link level entanglement generation. Okay, so now we reached the last topic that we're going to talk about, that is quantum network tomography. And the idea here is that we have a quantum network that might be formed by very different nodes. So you might have end nodes interconnected by satellites implementing quantum communication over large distances, and ground stations where the network has connections that are essentially ground and to ground connections, or ground to free space connections, and even free space to free space connections. So the key question behind quantum network tomography is how to characterize the links of a quantum network only utilizing end-to-end measurements. And the idea is that the end nodes of our network, which we see here as these computers with an atom inside them, they are allowed to perform quantum circuits. They can request the quantum network to distribute entangled states for them, such as a GHZ state, and they can also specify the circuits that will be executed by the intermediate nodes to distribute the required states. The intermediate nodes can receive requests for circuits to be used to generate end-to-end entanglement. They have access to ancilla qubits to help them distribute entanglement, but this is important, they are not allowed to perform measurements for estimation. And what is the motivation behind this? Well, we might have inhomogeneous quantum hardware in our networks together with hybrid communication media, but we still would be interested in characterizing links and performing network management. So for instance, it might be interesting for us to perform faulty network hardware identification without having to really have direct access to the network infrastructure. By doing so, and by being able to characterize, let's say, the noise introduced by the links of the network, we might be able to do improved decision-making when doing resource utilization and allocation. For instance, we might want to avoid particular links of the network if they are introducing a lot of noise to the entangled states they are generating. Moreover, one thing that we can do is that we can perform noise-informed quantum error correction, because in principle, we would like to have the description of the actual quantum channel in the mathematical sense that represents what is the noise process for each one of the links in the network. And this will allow you to improve decoding by knowing what errors are more likely to occur. one thing that I think it's also pretty cool is that if you can do network characterization in an end-to-end way, you can do quality assurance. For instance, imagine that you are paying for some service for a quantum internet service provider, and you would like to validate if that service that you're getting is actually the service you're paying for. If you can do that, the sort of characterization, without relying on the direct access to this or the quantum service provider to tell you how the network's operating, you can do some sort of quality assurance. And also, you can implement reconfigurable applications that change their behavior based on the levels of noise of the network at a given point in time. Okay, so let's proceed. Let's again take just a quick look at our operational assumptions. We have end nodes, and essentially what the end nodes are doing is using the network to generate end-to-end entangled states. And we have intermediate nodes that are receiving requests for circuits to be distributed. They have access to installed qubits, but they really cannot be used to do direct measurements for estimation, meaning an intermediate node cannot simply measure a qubit for you and give you the answer, so that you do estimation on the channels that are interconnecting that node to the rest of the network. Our model is as follows. Again, we're going to use a graph to represent the network, where the nodes of this graph are quantum processors, and the edges of this graph are representing the quantum links that we use, such as fiber optics and free space channels. We have end nodes and intermediate nodes. In this figure, the end nodes are nodes A, B, C, D, and E, and the intermediate nodes are nodes F, J, K, and L. The links are single qubit quantum channels that we assume they are Pauli channels, and we're going to assume a one-way quantum transmission just for the purpose of easiness of exposition. It will be easier for us to see how tomography works by looking at a one-way architecture, but you can essentially do whatever I'll discuss from now on in a two-way architecture as well, by modifying some things here and there. Remember also that Don stressed in one of his slides that one and two-way are completely equivalent services to be implemented by a quantum network in terms of what they can accomplish. So our goal here in tomography is really to estimate the probabilities associated with the Pauli channels in the network by relying on end-to-end measurements exclusively. And let's see how we do that, how we can characterize stars, quantum stars, we'll see what they are right now, where the error model is a bit flipped. So let's look at this very simplified topology where we have three end nodes interconnected by a single end node, essentially a quantum star network. And each one of these links is a special type of a Pauli channel, a bit flip channel, that works as follows. If you send a 0, you can get a 1 with probability theta sub e. If you send a 1, you get a 0 with probability theta sub e. So the way we can do network tomography in this particular network goes as follows. There are actually many ways, but today I just like to focus on one way that will allow us to see how this unfolds. So the way you're going to do this is by determining this probe circuit called the independent encoding circuit that determines how the intermediate node would distribute multipartite entanglement among these three nodes here in the following way. So we're going to start with the red node here, V0, preparing a Bell state 0, 0 plus 1, 1, sending one of these, the qubits of this Bell state, to the intermediate node. It will process the qubit that it was stored there, applying this quantum gate here, X, H, X. The intermediate node processes the qubit that we received, applying the quantum gate ZHZ. Then it performs a T-naught with a qubit that it is initialized in state 0. And recall that we allow the intermediate nodes ancilla qubits. So this is an ancilla qubit that was initialized to state 0. And then the outcomes of this 2-qubit circuits are simply transmitted to the remaining nodes in the star. And then all qubits are measured so that we can perform estimation. How this goes? Well, we do these measurements, but there's 2 ways we can measure this. If we assume we have pre-shared entanglement, meaning magically we had entangled states generated between the nodes before we do all this transferring process, we can do a GHZ measurement on these 3 qubits, or that is very similar to a GHZ fusion, essentially, and use the outcomes of this GHZ measurement to detect or estimate the probability for each one of the links. If we don't have access to this type of pre-shared entanglement, we can actually repeat this process twice and do local measurements on these qubits. There's no entanglement required for these local measurements. And then again estimate the bit probabilities for all links. And this actually occurs because this encoding circuit does some very an interesting manipulation with the state of the qubit that has been generated, such that the probability that you measure a 1 in these nodes, it's actually the probability that a flip occurred in each one of these links. So if a flip occurred in this link here, this qubit will measure 1. If a flip occurred in this qubit here, this qubit will measure 1, so on and so forth. In this case, when you're doing the GHZ basis measurement. So in the GHZ basis measurement, this is essentially what happens. Again, you don't need to do a GHZ basis measurement. You could do this by performing some local operations, but essentially the entangled measurement, this measurement that requires entanglement is more powerful than the local measurement alone. Okay, and can we actually use this idea to actually characterize more complex networks now that we saw how we can actually use this to figure it out what's happening on a star network of a bit flip? And the answer is yes. This sort of state preparation or distribution algorithm that I was, or circuit that I was telling you, actually generalizes for rooted trees of your network. So instead of having just one star, you can have a tree and do this type of entanglement distribution over a tree. And you can characterize the links in the tree and then characterize graphs by performing a tree covering of your network, meaning you find multiple trees so that each link lies on at least one tree, and you characterize the tree. And once you characterize all the trees, you get a characterization for all the links in the network. Again, what is nice about this is that it's compatible with both one-way and two-way architectures, even though we really just focus on one way because it's easier to see the generation process happening. This is still a very active area of research with plenty of open problems that people are investigating. Okay, so let's go over our last poll question for our course, that is poll question 13. What are the key aspects of quantum network tomography? Select all that apply. A, it relies on end-to-end measurements to estimate parameters for quantum network links. B, it requires pre-share entanglement among n nodes. C, can only be implemented in one-way quantum networks. D, can characterize complex network topologies by partitioning networks into trees. Or if you'd like to answer, I don't know, that's option E. Okay, so let's see the answers. I think, yeah, most people selected the correct answers. That is, network tomography does rely on end-to-end measurements to estimate parameters for quantum network links. And it can characterize complex network topologies by doing tree partitioning. I showed you one way that you use pre-shared entanglement among n nodes to do a measurement. But as I said before, it is not required. there is a way that utilizes it, but you can get rid of that by performing the generation circuit twice or many times, depending on the type of entanglement that the measurement you need. And as we saw before, you can implement this in both one way and two way. Okay, so I think that now maybe Don can come in and do a quick recap with you all of the course so far.
Go ahead, Matheus.
Oh, okay. So what we saw today was really a set of topics that relate quantum and classical networks. We started with the fundamentals of quantum communications, where we saw the concepts of a Bell state, of repeater chains, of distillation, fidelity, so on and so forth. And we then talked about scheduling in quantum repeater chains. Essentially, we saw three different types of entanglement swapping schedulings: sequential, swap ASAP, and nested entanglement swapping. And we compare their performance based on different characteristics of quantum repeater chains. Then we migrated to comparing classical and quantum networks in a more detailed way, where we saw how the internet was developed and designed and how the structure of the internet goes. We saw how to do reliable classical and quantum communications and how they compare to each other. We also looked at a protocol stack for both the classical and quantum internet, understanding how the different layers operate so that we can implement efficient end-to-end communication in both classical and quantum. We also looked at routing and how we perform routing decisions by mapping a network into a graph, and where the nodes are where the vertices of the graph are the quantum network nodes, the edges are the links, and how we compute paths among network nodes so that we can perform implement communication among them. We also looked at a way to come up with a connectionless quantum network architecture that builds on the stack, or that it was evolved from the stack, the classical internet stack. And we saw the pros of having a two-way connectionless quantum network architecture that are things like you can utilize most of what was developed for classical networks and apply to quantum to solve problems that are very meaningful to the performance of quantum networks. And finally, we ended the course discussing quantum network tomography, that is essentially defining methods for the estimation of network links when we only allow us to do end-to-end measurements for estimation, such that the internet infrastructure is not directly accessed to perform estimation and to derive expressions or calculate parameters that characterize the network links. And with that, I think we would like to thank you all for staying with us here for this 3 hours and 5 minutes approximately, and for all the questions and comments and your participation. And again, if you have any more questions, yes.
Yeah, I'd like to extend my thanks as well.
And maybe I can stop sharing, and in case people have additional questions, I'm happy to answer them live. I think Don and I covered most of the Q&A. I think there's one there.
There's one.
One here. Okay. So if I understood correctly, I think that the way you do this, that you do this type of heralding, is by adding classical information. And in this case, let's say if you are on a quantum datagram, if that is what I understood, the quantum datagram has a classical field that will allow the nodes to detect which qubits are paired with each what other qubits. And in the one-way network tomography setup that I showed you, you can still do that by sending classical information around and having this sort of a pairing of a qubit and the classical information regarding that qubit to actually do this type of bookkeeping that it will allow you to do this type of differentiation that I believe it's what the question is asking. I don't know, Don, if you'd like to add anything.
I'll add that you need to have sort of a pretty good time synchronization between the two nodes. And if you do, then by the timing, you would know which qubit belonged to which qubit. Another way is if they were generated with different wavelengths, then of course you would just know what wavelength you had received and then herald at that wavelength. Uh, we're not experts in the time synchronization, but our understanding is that that is feasible. It's doable for quantum systems. Okay, thanks again.
Yeah, thank you all.